Okay, so this is sample problem 17.2. Starting with a 1.00 liter of, or starting with 1.00 liters of a buffer solution, that's 1.00 molar in acetic acid and 1.00 molar in sodium acetate. Calculate the pH after the addition of 0.100 moles of sodium hydroxide. Assume that the addition does not change the volume of the solution. So we have a buffer, we have acetic acid, and I'm going to go ahead and calculate the number of moles. The number of moles of acetic acid would be, well, the volume is a liter, and the molarity is 1.00 moles per liter. So that's 1 mole. This problem makes all the numbers nice and easy. We also have sodium acetate, right? So sodium acetate, CH3, COONA. The acetate is this part right here. That's the conjugate base. The number of moles of that, again, 1 liter times 1 mole per liter. So 1 mole, again 1 mole. They're making things nice and easy. So now we're going to add sodium hydroxide. And the number of moles of that is how much? 0.10. Actually 0.100 for some reason. Okay, so there's the number of moles of sodium hydroxide. So here's what you do. The equilibrium is between these two. Buffers have an equilibrium between the weak acid and its conjugate base. So those are the two active ingredients in terms of the buffer. But the sodium hydroxide is going to affect the pH. We're adding sodium hydroxide. So we have to first decide what's the sodium hydroxide going to react with. This is a base, right? This is an acid, and this is a base. So which of those two is the sodium hydroxide going to react with? It will react with the acid, right? It's going to react with the acetic acid because acids react with bases. So, acetic acid reacts with sodium hydroxide. Notice for this one I'm going to leave the states of matter out just to simplify the writing, okay? Now, how do we deal with acid-base reactions when you have something like this? It's not that unusual or not that a bad idea to think of it as a double displacement reaction. Acid-base reactions are often double displacement. So the sodium combines with the acetate. There's two parts here. Think of acetic acid as acetate and hydrogen. Acetate and hydrogen. Sodium hydroxide. So switch partners. The sodium goes with the acetate part, and the hydrogen ion goes with the hydroxide to form water. So you get a CH3, COONA, sodium acetate, and then you get H plus and OH minus, which is water. Now, this is a buffer problem, so let's not lose tracks here. If this is a buffer problem, we should be able to use the Henderson-Hasselbalch equation. Oops. pKa plus the log of the concentration, the ratio of the concentration of the acetate over the acetic acid. Okay? So all we really have to do is find out what those two concentrations are after this reaction takes place, add that to the pKa, you got your pH. Okay? And that's really what they're asking us to do. So let's put the amounts in. The acetic acid, the amount of that we have is 1 mole. The amount of sodium hydroxide is 1/10 of a mole. And the amount of sodium acetate is also a mole. We don't need to worry about water in this case. It's a liquid. Limiting reactant problem. Subtract the smaller of the two reactants. Don't forget to add it to the product side. Okay, So this goes down to 0.9 moles. This goes down to 0 moles. So all the sodium hydroxide is gone. Oops. And the sodium acetate goes up to 1.10 moles. So now the molarity can be found by dividing by the volume. So if we take the number of moles and divide that by the volume, 1 liter, we get 0.90 molar and 1.10 molar. So now we got the concentrations. Now we can plug this into the Henderson-Hasselbalch equation. The pKa of acetic acid, we could either look that up or we could calculate it. The negative log of the Ka is 4.74. Plus the log of the ratio of the concentration of the acetate, which is 1.10 molar, divided by the concentration of the acetic acid, 0.90 molar. So let's figure that out. I'm going to work backwards just for the calculator's sake. I'm going to say it's 1.10 divided by 0.90. Okay. Concentration of the base over the acid. Take the log of that. And then I'm going to add to that the pKa, 4.74. 4.83. Look what happened to the pH. It only went up a little bit. It went from 4.74 for the buffer up to 4.83 because we added some base. So it should go up a little bit because we're adding a strong base. But it doesn't go up very much. So this is really acting like an excellent buffer. Now you may have thought about this. If we made the number of moles of sodium hydroxide larger, 0.5 or 0.6, the pH would change more dramatically. But because it's a very, very small amount of sodium hydroxide compared to the amount of acetic acid that's in the solution, only 10%, the pH doesn't change very much.